Alright, we're going to look at AP Rectangular Approximation Method and Trapezoidal Approximation Method problems. So in these problems, we're often given a table of values. So here I'm given this table where t is in minutes, and I have this function h of t in degrees Celsius. And I'm told that as a pot of tea cools, the temperature of that tea is modeled by a differentiable function h, for times between 0 and 10. So we have this pot of tea that's cooling down, and we're given the temperature of the tea after so many minutes, where time is measured in minutes and the temperature is measured in degrees Celsius. So values of h of t at selected values of time t are shown in the table above. So there's always going to be a written description of the table. So we can see that at time 0, the pot of tea was 66 degrees Celsius, and as time goes on, the pot of tea is cooling, which should make sense in the context of a pot of tea that's hot. It's going to cool down to room temperature. So now, part A. So part A is not actually a rectangular or trapezoidal approximation, but it's good review, and it shouldn't take too long, so we're going to do it. Part A is asking us to use the data in the table to approximate the rate. So we're going to approximate a rate, an instantaneous rate of change, approximate that, at which the temperature of the tea is changing at time 3.5. Show the computations that lead to your answer. So I can't find an instantaneous rate of change at 3.5. If I look at this table, the table has the instantaneous temperature, not even the instantaneous rate, but the instantaneous temperature only at these 5 values. And I'm trying to approximate the rate of change, so I'm trying to approximate the derivative. And of course, I do that with the average rate of change formula. And since I want to know what's going on at 3.5, and that's halfway between 2 and 5, those are the values that I'm going to use in the average rate of change formula. So for part A, normally we learn the formula with f, but there's no f in this problem, so it's going to be h of 5 minus h of 2 over 5 minus 2. And so I'm showing the computations that lead to my answer. I don't just want to write a numerical answer. I want to show where it came from. So this is like my f of b minus f of a over b minus a. So in other words, you wouldn't have to write this, but I'm writing this just for clarification. This is approximately h prime of 3.5. So approximate the rate. So the rate is the derivative, so approximate that using the average rate of change formula, and I can get this information from the table, right? H of 5, so H of 5 is 52, and then H of 2 is 60, and then over 5 minus 2. So one of the things I want to just point out here is that because this is an AP free response question, we can and should stop right here. So once I have a numerical answer, I can go ahead and stop and not simplify. So in this step right here, I didn't have a numerical answer yet. H of 5 is not a number until I replaced it with 52. So I could leave my answer, and should leave my answer, as 52 minus 60 over 5 minus 2. Because if you were to make a simple algebraic mistake from one step to the next, you would lose the answer point. So we would go ahead and leave the answer. This question does not need units, so we don't have to include them, and we could just stop right here. So here's the computation that leads to my answer, and here's my numerical answer, and that's it. I'm done. So now we'll move on to part B, which is actually trapezoidal approximation. But first, we're asked to use correct units and explain the meaning of this quantity here, 1 over 10, the integral from 0 to 10 of h of t dt in the context of this problem. So in other words, I have to talk about this pot of tea that's cooling down. So we're going to do that part first. I'm going to go ahead and use this space over here to do part B. So I'm going to explain what 1 over 10, the integral from 0 to 10 of h of t dt means. Alright, so what is going on here? First, we're going to go ahead and interpret this portion here. So we wouldn't actually have to write all this out. I'm explaining it to you right now what this means. So this portion here, this integral, represents the area under the curve h between 0 to 10. So and this information on this table, if we were to graph it, so here's t and here's h of t, and I have all these coordinate points, so 0, 66, and then 260, and 552, right here, all these points, and I cannot actually connect the dots, so I'll just sort of sketch connect the dots. So I'm going to have this function here, and from 0 to 10, if I had the exact function, the area underneath that curve would be this integral. So the integral from 0 to 10 of h of t dt is a definite integral. It's the exact area under the curve. But in terms of the context of the problem, well, this time right here was in minutes. So this portion t is in minutes, and this height h is in degrees Celsius. And when we find area, we multiply base and height. So the units of this area here is, if I multiply degrees Celsius times minutes. So the units of this quantity here is degrees Celsius times minutes. And that's kind of a weird unit, right? So it's not very typical. But what we haven't taken into consideration yet is, what is this 1 over 10 thing in the front? So remember that the integrals are adding up all of that area, right? So we started by adding up a finite number of rectangles to find the exact area, or to find an approximation for the area under the curve, but the bottom line is we're adding up a bunch of stuff. So one way we could think about this 1 over 10 is instead to think about dividing this definite integral by 10. So 1 over 10 is really division. So I have all of this area. I added up all of the area from 0 to 10, and then I divided by 10. So when you think about what happens when I add two numbers and then divide by 2, well, I found an average. So in this case here, that's what I have found, is an average. The integral from 0 to 10 is I added up everything from 0 to 10 and then divided by 10, which creates an average. But an average what? So now we're going to keep going with our units. So 10 is that amount of time that has passed. So this integral's units are degrees Celsius times minutes, but then I have times 1 over 10 minutes. So 1 over minutes times degrees Celsius times minutes is going to have the minutes cancel. So the actual units of that whole quantity here is degrees Celsius. So what I found is the average degrees Celsius, or the average temperature. So what does this whole thing represent? This is the average temperature of the T between 0 and 10 minutes. That is what this quantity here represents, the average temperature of the T between 0 and 10 minutes. So the average part came from the 1 over 10, and then we knew it was a temperature because we could think about the units. So first the units of the definite integral, then the units of the 1 over 10 averaging part in front. So now we found, or we explained what this means. Now let's actually find what it is. So, or approximate what it is. That's the second part of the question, is use a trapezoidal sum with the 4 subintervals indicated by the table to now estimate this value. So I can't find it exactly, but I can approximate it. So I'm going to leave myself some space here. So 1 over 10, the integral from 0 to 10 of h of t dt is, or I should say, is approximately. So I have to be careful and leave the 1 over 10 part. That's going to stay there. What I'm going to approximate using trapezoids is I'm going to approximate the definite integral. I'm going to approximate the exact area under the curve by using trapezoids over the 4 subintervals. So this is 1, 2, 3, 4 subintervals. And what I want you to observe here is that these subintervals do not have a uniform delta x. So the space between my input values is not the same. So between 0 and 2 is 2 units. Between 2 and 5 is 3 units. And I can just stop right there. Once one of them is not the same consecutively, I do not have a uniform delta x. So I have to compute the area of each trapezoid separately. So I have 4 trapezoids here. So 1 over 10 stays in front. And then I'm going to put a big set of brackets. And I'm going to have to do the area of 4 separate trapezoids. Now, the area of a trapezoid is 1/2, and then I'm going to have a height, base 1 plus base 2. So the height is going to be my first delta x. So my delta x1, the difference between 0 and 2 is 2. And then base 1 plus base 2 is going to be 66 plus 60. So 66 plus 60. So this is like h b1 plus b2. So that's the formula for the area of a trapezoid. So that's my first trapezoid. I've handled this portion here. So now I need to move on to this next trapezoid where the height is 3. So the difference between 2 and 5 is 3. And now these are my 2 bases. So plus 1/2. My height is 3. Base 1 is 60. And base 2 is 52. And then I'm going to keep going, and I'm already out of space, so I'm going to write below here. My next trapezoid is 1/2. H this time is 4, so the difference between 5 and 9 is 4. And then my next 2 bases are 52 plus 44. And then my last trapezoid is 1/2. The next height here is 1. Between 9 and 10, the difference is 1. And then I have 44 plus 43 as my final 2 bases. And now, the great thing about AP free response is we do not have to, nor should we, simplify. So this whole thing is it. This is the answer. And this problem is just a little bit trickier because I can't use that little shortcut where we double all of the middle terms because it's a trapezoid, right? I can only use that rule if I have a uniform delta x. So the delta x1 right here is 2, and then it's 3, and then it's 4, and then it's 1. So I have no uniform delta x. So I can't use that little shortcut where I would say 66 plus 2 times 60 plus 2 times 52 all times delta x, because there is no delta x. There are 4 delta x's in this case. So I have to compute each trapezoid individually. Alright, next problem. And in this problem, we're going to interpret the word Riemann to mean rectangular. So I have this table of data. I'm told the temperature of water in the tub at time t is modeled by a strictly increasing twice differentiable function w. So remember, we've talked about this. Twice differentiable just means that you can take w's derivative twice. We're not given a second derivative. Where w is measured in degrees Fahrenheit and t is measured in minutes. At time 0, the temperature of the water is 55 degrees. So we can see that in the table. So at time 0, the water is 55 degrees. At 4 minutes, the water is 57.1 degrees. So we can see that happening. And we know that this is increasing, not because of the values in the table, because we were told that the temperature is increasing. And the water is heated for 30 minutes, beginning at time 0. Values of W of t at selected values for the first 20 minutes are given in the table above. So there's my description of the table of data. And in part A, we're asked to use the data in the table to estimate W prime of 12. So I'm trying to estimate an instantaneous rate of change. So without having the actual value of W prime of 12 or the actual function W to take the derivative of to be able to plug in 12, I'm going to, just like last time, use the average rate of change formula. So W prime of 12 is approximately W of, so 12 is between 9 and 15, so those are the values I'm going to use in my average rate of change formula. W of 15 minus W of 9 over 15 minus 9. So show the computations that lead to your answer, and then we're going to use correct units to interpret the meaning of my answer in the context of the problem. So here is the computations that lead to my answer. Then I have to substitute in W of 15. right? So I actually need numbers. So 67.9 minus 61.8 over 15 minus 9. So I do not and should not simplify this, just in case I don't want to make a simple mistake. But this time I do have to include units. And so now let's go ahead and think about the fact that in the numerator we did 67.9 degrees Fahrenheit minus 61.8 degrees Fahrenheit. So if I subtract two temperatures in degrees Fahrenheit, the numerator is still degrees Fahrenheit. And then 15 minus 9, I'm subtracting minutes, so that's still going to give me minutes. So notice what I have here is I have a rate. So this would simplify to a particular number. So what we found, what we're going to explain, the meaning of our answer is we have found an approximation for the rate of change of the temperature of the water at 12 minutes. So this quantity is approximately the rate of change of the temperature of the water at 12 minutes. So that is what our answer actually represents. So it's the approximate rate of change of the temperature of the water specifically at 12 minutes. So now let's go ahead and do part C. So part A was really just a review. And part C is saying between 0 and 20, the average temperature of the water in the tub is 1 over 20, the integral from 0 to 20 of W of t dt. So we talked about that idea last time, right? This 1 over 20 in front is the averaging component. So they're actually telling us that here. And the question itself says to use a left Riemann. So as I said, we're going to think of Riemann as rectangular. Use a left Riemann sum with 4 subintervals indicated by the table to approximate 1 over 20, the integral from 0 to 20 of W of t dt. So we're going to do that part first. We're going to ignore the second part of this question for now. So 1 over 20, the integral from 0 to 20 of W of t dt is approximately, so I have to bring down that 1 over 20, because the part that I'm going to use the left Riemann sum on is the definite integral. So 1 over 20 stays, and then now I have to do a left rectangular sum with 4 subintervals. So I go to my table, and what I have to recognize is that just like last time, there is not a uniform delta x. So here are my 4 subintervals, and between 0 and 4 I have 4, and between 4 and 9 I have 5. So I basically just have to stop right there and recognize that I have to compute the area of each rectangle this time separately. So last time we did the area of each trapezoid separately. Here I have to do the area of each rectangle separately. So here's 6, and then here's 5. So now, this first rectangle, so remember rectangles, the area is base times height. So the base, in this case, is 4. And then I have to decide on the height. Well, because I have a left Riemann sum, so here are my 2 heights, 55 and 57.1 as a possibility, but the one furthest to the left, as we move from left to right on a graph, 55 is the leftmost height. So 4 times 55 is the area of the first rectangle. So it's the base times the left height. And then the second rectangle, so I do each one separately and I add them. So this next one is 5 times the left height is 57.1. So between these 2 heights, 57.1 is on the left, plus 6 times the next height, again on the left between these 2, is 61.8. And then plus the next base between these 2 is 5, and the next height is 67.9. And then I'll close my brackets. So I would add all of these together. These are all of the individual areas of the rectangles. And then I'd multiply that by 1 over 20 or divide by 20, and that's going to approximate this average temperature of the water in the tub between 0 and 120. So what I can't do, just like last time, is I can't use my shortcut, right? So my little shortcut for left rectangular approximations only applies when there's a uniform delta x. And in this case, because there's no uniform delta x, so we'll write it again. So there's no uniform delta x, or in this case, delta t, right? I can't do that whole delta x times just add up all the left values and skip the right value. So we've answered the first part of the question right here. And the next part says, does this approximation overestimate or underestimate the average temperature of the water over these 20 minutes? So here's where we have to use that piece of information that we were explicitly told, that this function w is an increasing function. So I'm just going to quickly sketch an increasing function right now. So if I use a left rectangular approximation, well, that means over every little interval I go to the left endpoint and create my rectangle. So if I do that just a couple times on any old graph, if I draw a left endpoint approximation, I can see that I am an underestimate for the actual area because I'm missing all these little pieces here. So it's more clear if I go one more. So over any little interval, if I choose the left endpoint, I'm an under approximation. So I'm going to choose underestimate. Explain your reasoning, because h of t is strictly increasing. And that's all I have to write here. So over or underestimate, so I'm going to be an underestimate, and because h of t is increasing. So it's just knowing this information. And notice I didn't even bother really memorizing it. I'm really just going to understand what it means to be increasing and what a left approximation means in terms of the drawing of the graph. All right, next question. So we can see we have another table of values. So whenever I see a table of values, I should really get used to, at this point, similar types of questions popping up. So we know we're probably going to have to do either a rectangular or a trapezoidal sum. So I have the volume of a spherical balloon expands as the air inside the balloon is heated. So the radius of this balloon in feet is modeled by a twice differentiable function r. So again, that means r, we can take its derivative twice. T is measured in minutes. And between times for 0 and 12, the graph of r is concave down. So we were given this piece of information. The table above gives selected values of the rate of change r prime of t. So that's what makes this problem slightly different, so I want to go over it. We're given now a table with a rate. So t is in minutes, but r prime of t is already in feet per minute. So the radius of the balloon over time t, over the time interval between 0 and 12, the radius of the balloon is 30 feet when t equals 5. So what I've been given in this last statement, the radius of the balloon is 30 when t equals 5. So r of 5 equals 30. And that's not in the table, right? So notice r prime of 5 is 2. So exactly at 5 minutes, the radius is 30 feet. So the difference is that exactly at 5 minutes, the radius is growing 2 feet per minute. But right at 5, the radius is 30 feet, right? So those are the two different pieces of information we were given exactly at 5. Now, I don't actually want to go through and do every single one of these problems, but I do want to talk about them to show that we can actually do all 3 parts of this problem already. So part A, it says, estimate the radius of a balloon when t equals 5.4 using a tangent line approximation at t equals 5. So here, the strategy is I need a tangent line at 5. Well, if I need a tangent line at 5, I need a point at 5, which, hey, that's what we just wrote down. My point is 530, and I would need a slope at 5. Well, a slope is r prime of 5, which, again, we talked about, is 2. That's r prime of 5. So I'm just going to write that real quick. R prime of 5 is 2. So I could find a tangent line, because there's my point and there's my slope, and then I would use that tangent line to approximate the radius when t is 5.4. So I would find that equation, y minus y1, etc., find the equation, and then I'd plug in 5.4 to estimate the radius of the balloon at 5.4. So I'm going to challenge you to do that on your own in your notes. That's definitely a question that could pop up on a quiz or a test, absolutely, because it is review. And then the second part of the question is your estimate greater than or less than the true value? And for that part, the hint I'm going to give you is that you were told r is concave down. So I want you to sketch a concave down function and sketch a tangent line on a concave down function, and then answer whether or not the estimate is greater than or less than the true value. So I basically set you up on how to do the problem and encourage you to do the problem. In part B, we're asked to find the rate of change of the volume of the balloon with respect to time. So this right here is telling you in fancy words to find, hopefully you said it as I'm saying it, the derivative. So find the rate of change of the volume with respect to t. So find the derivative with respect to t when, so at that exact moment, at the instant, t equals 5. Well, here's my volume formula. So I'm asked to differentiate it, take the derivative of this thing with respect to time, and then go ahead and plug in 5. So that is what I'm asked to do in this particular problem. There is a little bit of a trick to it, but again, I encourage you to do it as well. It involves the trick, and I will tell you, involves implicit differentiation, because I'm taking the derivative with respect to t. Notice there are no t's in this problem. So again, go back, encourage you to work on that. But we are going to do part C together. Use a right Riemann, again, Riemann rectangular. Use a right rectangular sum with 5 subintervals indicated by the data in the table to approximate the integral from 0 to 12 of r prime of t dt. So this is what we're trying to approximate. And then we're going to explain what this even means. So first let's find this. So there's no average involved. There's not going to be a 1 over 12 because that's not there at all, no average. So we want to find a right rectangular sum with 5 subintervals. So I need to see, well, can I use my shortcut? Is there a uniform delta x? So if I look at this, is there a uniform delta x? So I want you to think about what your answer is there. And the answer is no, there's no uniform delta x, or in this case delta t. The difference between these two is 2, between these two is 3. And so right away there is no uniform difference between the input values. So I have to do each one separately. And I this time want to use a right Riemann sum. So I'm going to go ahead and do each area of each rectangle separately. So the base of the first rectangle is 2, and the height, so I choose between these two values, and the one on the right hand side is 4. So 2 times 4 plus 3 times, so now 3, that's because that was the base, and the height, I choose the right height, which is 2. So 3 times 2 plus 2, so I'm looking at this base here, and the height I'm going to choose is 1.2, because I'm looking at these two heights. The right height is 1.2, plus 4 times the right height is 0.6, and then plus finally 1 times 0.5. So again, I had to do each one separately because the delta x was not the same. Excuse me. And again, AP free response, I don't need to simplify. This is my answer, at least to the first part. But now, using correct units, explain the meaning of this integral here. So integrals, remember, are area under this curve, r prime of t. So let's just think about the units. If I were to plot t and r prime of t, well, t is in minutes. So remember, I have 0, 5.7. So I'll just plot a couple of these values, 2, 4, 5, 2. This is happening. So this base here is in minutes, but these heights here are feet per minute. So this is already a rate. And so I'm finding the area using right endpoints. So I'm finding, this area here of these rectangles. Well, area again is base times height. So the area of each of these is units of base minutes times the height in this case is feet per minute. So what happens to the units is that minutes cancel, and I end up with just feet. So I'm doing this to give you a basis for understanding why our explanation is about to be what it is. So when I find area, which is again an integral from 0 to 12, under this particular curve, r prime of t, so this maybe was the actual curve, I'm finding area that represents feet. So what does this thing actually mean? The integral from 0 to 12 of r prime of t dt is let's think about what was happening. Well, this hot air balloon was expanding at this particular rate. So this is the amount of feet the radius has expanded. So the radius of the balloon has expanded between 0 and 12 minutes. It's that quantity, it's that amount. So when I find the integral of a rate, I find that quantity. So from 0 to 12, if I integrate that rate, I'm going to get the total amount of feet that the radius of the balloon expanded between 0 and 12 minutes. Alright, another problem. So I have hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t between 0 and 6 is given by a differentiable function c, where t is measured in minutes. Selected values of c of t measured in ounces are given in the table above. So I have, as time goes on between 0 and 6, how much coffee in ounces is in the cup at these respective times. So I have all 4 parts of the problem up here, and we're actually only going to do part C. But I have all 4 parts up and in the notes because we can now officially complete an entire free response AP question. We have the tools to be able to solve all of these. So that is my challenge to you. This is a great question to have on a quiz or a test, is to go through and to complete the other parts of the question with the prior knowledge that we have. So the part we are going to focus on only is part C. So part C says use a midpoint sum with 3 subintervals of equal length indicated by the table to approximate the value of 1 over 6, the integral from 0 to 6 of c of t dt, and then explain what this means. So I'm going to go ahead and bring the 1 over 6 down because we're going to use a midpoint rectangular sum to approximate just the definite integral. So 1 over 6 times. Alright, and so now I can go ahead and look at this table here, and I'm only to use 3 subintervals of equal length. So if I go from 0 to 2, from 2 to 4, and 4 to 6, I have 3 subintervals of equal length, and that equal length, or that delta x, equals 2. So here is the first problem on these that we've done so far that does have a uniform delta x. So my uniform delta x in this case is 2, so that is delta x. And because I have a uniform delta x, now I can use the shortcut where I add up the midpoint heights. So I'm going to add up the midpoint heights. So the number of things I'm adding up is the number of rectangles I'm trying to add, which I was told is 3, right? I'm using 3 subintervals. So my base is 2, right? 2, 2, and 2 every time. But to decide the height, well, I need the midpoint between 0 and 2. So halfway between 0 and 2 is 1. Halfway between the next one, 2 and 4, is 11.2. And halfway between 4 and 6 is 5, which height is 13.8. So remember that the output values are the heights, and the difference between the input values are my bases. So my base was always the same at 2, so now I need only add the midpoint heights. So 5.3 plus 11.2 plus 13.8. And then close my bracket, and there's no need to simplify. So this is the approximation for this quantity. Now we have to explain what this quantity represents. So hopefully we remember, because we've done this earlier, that this quantity is going to represent an average for what? So in the context of the problem, what is this representing? So it's the average amount of coffee is the average amount of coffee in the cup between 0 and 6 minutes. And again, where is this coming from? So we'll just do a quick sketch. Well, the input is time in minutes, and the output, C of t, is in ounces, and we're finding that area, if you remember. So it looks, the actual graph looks to be maybe like it's increasing, but that doesn't matter. So we're trying to find the area here. So we're finding, the area of different rectangles, and that area is base times height. So this portion here is, let me write the units on top in a different color, is multiplying base times height units, so ounces, times minutes. So that's the units of this portion here. And then 1 over 6, well, 6 is in minutes, so we have 1 over minutes. So what's going to cancel is the minutes. So what we have left is ounces. So this whole quantity represents the average amount of coffee, because coffee is in ounces, in the cup between 0 and 6 minutes. So it's that whole idea of units. Understanding the units of area is really going to save us in all of these problems.